It's my privilege to introduce the next speakers, Joanna and Nevin, and their project is titled Design Purposes of Flow 4 phenyl-N 9' acridinyl-hydroxylamine.
Okay, so our research is on the design purposes of Flow 4 phenyl-N 9' acridinyl-hydroxylamine.
Our mentors were Matthew McDonald and Bella Walden.
My name is byNevin.
And I'm Joanna.
Okay, first we have some background information. So what is cancer? So cancer is one of the leading health concerns in the world, and it's caused by abnormal mutated cells which are able to divide faster than normal cells. So these cells then begin to cluster together and they form tumors, and these tumors are known as malignant or benign tumors. The malignant tumors being cancers. So these cancer tumors then start going through a process called metastasizing, where they're able to expand to the rest of the body and which is very bad. So around 12.7 million new people every year are affected by cancer, and as you can see by the diagram, right, the projected new cancer cases is only increasing. So although the mortality rate has decreased by 13% since 2012, there's no need that better and more effective cancer treatments are needed.
The existing treatments. Currently, the existing treatments are chemotherapy, radiation, and hormonal treatments. However, these come with a lot of side effects, including fatigue, hair loss, bleeding and bruising, and also lots of infections. They're also given to a patient at a very high dosage and can remain in a patient's body for up to 6 months after they're done with treatment. Topoisomerase. Topoisomerase is a very important enzyme in DNA replication. There are 2 different types of it. Type 1 inserts itself into DNA helicase and cuts one of the strands and aligns it that way. Whereas type 2 will insert itself and have both of the strands of the DNA helicase, as we do this picture. This is a different way that it works. Our drug that we are trying to synthesize lacks either work as a catalytic inhibitor or as a poison. If it is a catalytic inhibitor, it'll stop the topoisomerase from working, however, it'll still be in the cell. Whereas if it is a poison, it'll kill the topoisomerase altogether and it will no longer be in that cell. Previous research suggests that it is a topoisomerase 2 catalytic inhibitor.
Okay, so the compound we're trying to synthesize is known as the 9-aminoacridine. So the acridine group has existed for a while and it's been used as a dye. However, in the early 20th century, it was reevaluated for chemical properties and it was concluded that the acridine group had antimicrobial, antimalarial, anti-inflammatory, and anti-tumor properties. More recently, specific research was done on the 9-aminoacridine, and research was done on mice, and they concluded that the 9-aminoacridine was able to treat cervical and lung cancer in those mice. Now, the way the aminoacridine functions is as a DNA inserter. And what that means is that the aminoacridine will insert itself between the base pairs in DNA as it's unwound. And this interrupts a lot of the key biological functions in the cell, such as transcription, replication, and the DNA repair process. So interruptions in these processes it induces apoptosis in the cell. And this is why we're able to use the aminoacridine as an anti-tumor drug. So what is apoptosis? It's simply a term used for natural cell death. Apoptosis covers 2 unique functions, the first being an entirely regular process which happens in all normal cells. It just simply deletes any unneeded cells. Whereas the second process is carried out by CCL cells which go through the body searching for other harmful cells which could potentially be harmful for the body, and it induces apoptosis in these cells. Now cancer cells are able to evade that process, and they're able to evade this process because of a protein P53. Protein P53 is the apoptosis gatekeeper. It basically decides when apoptosis is induced when it's told to do so. And the research shows that the most common thing between different cancer cells is the missing and mutated protein P53.
Existing research. There's a lot of existing research that has been done on the 9-aminoacridine and its derivatives. Elizabeth Carlson, a student here at UNC, did a research project on a drug similar to ours, except for her drug had an extra oxygen carbon bond, as seen right here. That bond was very susceptible to hydrolysis. Hydrolysis is when water comes in and it breaks a compound apart into 2 pieces and makes it not able to work anymore. Because of that, this drug would not have lasted very long in a patient's body. However, it was still worked as an anti-tumor drug. Because of this, this film decided to make his own procedure where he eliminated that oxygen-carbon bond and made it a more effective drug.
Okay, so what's the purpose of our research? So what we want to do is expand upon the research done on this film, where he removed that carbon-oxygen bond that we just talked about, and added bromine element to this compound. We believe that adding that bromine element will increase the drug's ability to bind to DNA. So the bromine that will be added to the compound is known as substituent, and we believe that the bromine substituent will, like I said before, create a tighter bond with the DNA. This is because, as you can see in this figure, bromine is right here, and it's a weakly deactivating element. Now what that means when I say weakly deactivating is that bromine is electron withdrawing, so it's going to pull electrons away from the aminoacridine portion where the DNA circulation happens, and that's going to create a positive charge there. And since the DNA is negatively charged, the two should attract, and there should be a tighter, stronger bond. So why did we choose bromine? Basically, we knew that we wanted to choose an electron withdrawing element because we wanted to see a stronger bind so that a lower dosage would be required in when administering this drug. So we looked at our available resources and we found that the two withdrawing groups that we could use were either a nitrate group or a bromine group. So at this point, we had to look at the reactions that would be necessitated depending on the sums we used. So we examined the nitrate group reaction and it required a 15-hour stir maintained at 80 degrees Celsius, whereas the bromine reaction required a 1-hour stir, required at a 60 degrees Celsius. And what this means for us that since the 80 degrees Celsius would be much harder to maintain, especially over a 15-hour period, and so we decided to go with the bromine. In addition, we also looked at some research done by Josh, where he synthesized a phenyl-N, which is a compound that's required in the synthesis of the drug. And he was able to synthesize that compound with a bromine substituent at a 91% yield, whereas he's only able to create the nitrate substituent at a 70% yield. So we had a feeling that the bromine reaction would be more successful and better for our research.
Our methods. We designed our methods based off of research done by Gosh, Philosophy, and Design. Our methods became a four-step process with several other steps in between. We use three main steps for our procedure. The first one on the side is what we use for all our steps. We had a ground bottom box with a stir bar in it, and it was stoppered and it had a needle going through with argon gas to keep it under inverted conditions. It was also placed on a ring stand that was over a stir/hot plate. After that first step, we used a separatory funnel, and that would separate the organic layer from the inorganic layer. And then after every step, when we used a solvent, we used a rotary evaporator, where it would heat up the compound as a solution to remove the solvent and concentrate the product.
Okay, so the first step in our procedures was the synthesis of a triflate salt with a bromine element added. And so our procedures for this synthesis were outlined by Josh and Bassam, and they involved synthesizing or reacting a 1-bromo-4 iota of benzene with bromobenzene along with MCPBA and triplet acid using dichloromethane as a solvent to achieve the triflate salt. So these four were added to a 25 milliliter gum-bottom flask and stirred for 1 hour. And after 1 hour, we wrote about the solution and then add diethyl ether to the remaining compounds. Now the reason we do this is because what the diethyl ether is going to do is allow the impurities in our product to be dissolved into the ether, and the organic portion where our compound exists that we're seeking will remain solid. And when we place this in the fridge, the organic layer will crystallize, allowing us to synthesize.
Okay, for step 2, we have to do this immediately after step 1. Because step 1, the product of step 1, the triplet acid or the triflate salt, was very unstable. So we put that in the fridge and cooled it for 30 minutes. While that was happening, terpene oxide, DMS, and N-hydroxylamine were mixed together. When we did this, we came up with a red, fleshy-looking liquid. Once we added the triflate salt, we raised the temperature to 60 degrees Celsius and stirred it for 1 hour. We then took that solution and we put it into a separatory funnel. And we added diethyl ether and that deionized water. We then rinsed it with deionized water twice and then rinsed it with brine again. When we rinsed it with brine, however, the organic layer became a white milky solution. So we took that solution and we graphene filtered it to see if there was any precipitate in it, in which there ended up being some precipitate in it that was a white color. And so then we took the liquid that was left, which was a liquid that was yellow and clear. We added anhydrous sodium sulfate and we graphene filtered it again to remove the sodium sulfate. We then photographed it again and concentrate the compound.
So for the third step, we were going to hydrolyze the product from the second step, the N4-bromo-phenyl-N. Now there are multiple methods we could have run about this, but there were two in particular that we were interested in. One was outlined by this author's paper, and it was a base hydrolysis. But after further analysis of this, we found that several attempts proved unsuccessful, and decided to try we decided we would attempt the third method, which was a acid hydrolysis. So the acid hydrolysis, how we would have carried out the acid hydrolysis was we would have transferred our product from step 2 into a 100 milliliter round bottom flask, and to this flask we would have added 15 milliliters of lactic acid, and we would have added hydrochloric acid, and this would be heated to 50 degrees Celsius using a standard reflux setup, and we would add 1 milliliter of hydrochloric acid to this until the solution refluxes. At this point, we allow the solution to cool to room temp and make it alkaline by adding sodium hydroxide to the solution. And then this is suction filtered to create a precipitate. And then we would bubble hydrochloric acid through the precipitate to ensure that no extra precipitate is formed. And then this would be dried overnight.
For step 4, we would take a product from step 3 and stir it with 9-chloracridine. 9-chloracridine can either be bought commercially or be synthesized in a lab. It's more cost effective for a larger scale to be synthesized in a lab. And so the product from step 3 can also be bought commercially. However, that is also very expensive, so it's more cost efficient to make it. So we added the phenyl-hydroxylamine and the 9-chloracridine, and we raised it to a temperature between 80 to 100 degrees Celsius, and then we would stir it for 6 hours. Then that solution would be concentrated using a rotary evaporator.
Okay, so due to time constraints, we were not able to proceed with our procedures farther than step 2. And so, but we were able to analyze the product that we had created after step 2, N4-bromo-phenyl-N, and we confirmed that we had successfully synthesized this product at a 75% yield. We were able to confirm this using an HNMR scan. So what an HNMR scan does is it can show us the location and quantity of hydrogens in a given compound, and using this information we can figure out what product we've created. This is the HNMR scan from the product that we had created, and we compared this HNMR scan to the NMR from Josh's research, where he attempted to synthesize the same bromine substituted phenyl-N, and we found that most of the peaks from 7 to 8 are the peaks that resemble our product, and we found that most of those peaks existed in our NMR. For all of them, the few extras which resemble in impurity. So the largest peak right here is chloroform B, which is the solvent used when taking HNMRs. Apart from that, we have the labels made for the rated peaks, and they resemble the different locations of the hydrogen in the compound we were trying to make. But as you can see, there are other peaks, about 4, 2, and 1.3, and those peaks are impurities, which could be either because of unreacted hydroxylamide or side reactions or any other things like that. So for our product analysis, like I said, we took an HNMR. However, to make it easier to read and easier to identify the peaks, we supersaturated the NMR. And what that means was, instead of dissolving crystals in chloroform B, we added the chloroform B directly to our compound before taking the NMR, which means we expected larger, more identifiable peaks. But after seeing the NMR, the peaks were still small, which means that of the 75% yield we had made, not all of it was the product that we were seeking, as we saw by the impurities. And because of this, since step 3 was a longer, more intricate reaction, we decided we didn't have enough product to continue with the procedures.
Our observations from our procedure were not exactly what we expected, especially after step 2. During step 2, when we added the terpene oxide into the MS, we found that we had a red, slushy-looking liquid, which in some papers we had gotten in clear red liquid, which was not supposed to occur. However, we did not know why, because we had added everything properly. And then after we added the brine to our room in step 2, we ended up with a milky white solution for our organic layer. So we gravity filtered it and we came up with a precipitate. And that precipitate, we hoped that we didn't get any of our compounds that we wanted in that, so we took an infrared scan spectra. The spectra didn't come up with very many organic material identifications, except for between 3,000 and 4,000, there's a big dip. And that symbolizes that there was an oxygen-hydrogen bond, which we think came from the water that was still there. And then, since our compound actually had 2 benzene groups, we would have expected some fluctuation between 2,000 and 4,000 years older. There's something there, so we put that none of our products in the which left us with the only option that is really required from the brine.
Okay, so after we identify our standard minimum, we have to calculate our percentage. So basically, after NMR, since there was excess chloroform B left in the left to lose our compound, we had to rotogap it again to remove this excess. So after rotogapping the compound, we weighed the compound and calculated that percent yield to be 237%. And so obviously, this isn't a very realistic or possible yield. So we knew something went wrong. So we went back and we checked our balances and reanalyzed the product and found there was actually still more excess chloroform in our compound. So after rotogapping again, this time for longer and more thoroughly, when we were sure the crystals were dry, we reweighed the compound and we found that we had a 75% yield. We knew this was a much more realistic yield because, as I said earlier, Doc was able to synthesize a 91% yield in this product in a more professional lab setting.
Future studies. There are lots of steps that we can take for the future. One of the main ones being completing the procedure and seeing that we come up with the right compound. After that, it should be redone several times to see if we can get a higher concentration of it and also remove a lot of those impurities that we saw in the NMR. After that, we will also do an analysis of how the bromine constituent causes the compound to bind with the DNA differently. And because of that, we'll also go through other derivatives of the compound and see how those will affect it in other ways. Because our long-term goal is to see that we can make this drug an actual anti-tumor drug that other cancer patients will actually get to use. And so to do this, we need to make the drug have the least amount of side effects possible, the lowest dosage possible, but also the most effect in others in the body.
Okay, so we would like to thank Matthew Tom for his expertise in the lab and for helping us with all our procedures and for mentoring us and advising us through this process. We would also like to thank Saba Wolde for her assistance with our calculation, our lab work, and for supporting us with our project. We would especially like to thank Ben Schobler for his help with our NMRs and allowing us to analyze our device to see how our research went. And we would especially like to thank Excel Energy, Union Pacific, Timothy Frederick, Dr. Kevin and Mona Lear, and the Joseph family for sponsoring our participation in this program and allowing us to do this research. We would also like to thank Lori Ball, the director of SSI, for giving us this wonderful opportunity. Thank you. We will take questions.
How many trials did you guys do? The question was, how many trials did we do? We did 2 trials because the first time we did it, we didn't get a very good compound after step 2, and that compound had a lot more imperfections in it and impurities, so we did it again to see if we could make it more pure.
Yeah, so to add on to that, so after, like Joanna said earlier in the presentation, the product after step 1 was extremely unstable, which means that step 2 had to be completed immediately afterwards. On our first attempt of getting past the step, we actually waited one night because of time constraints before proceeding with step 2. So we suspect that some of the trifluoride salt has decomposed, causing more impurities in our final product, and the NMRs didn't show a solid, it didn't look like the phenyl-N compatibility. Yes.
Because of this structure, what makes four compounds different from like other like
amino acids. So other than amino acids specifically, our compound, the main difference is that added bromine, and what that's going to do is make it bind more tightly with the DNA. So you could be experimenting with other functional groups, which could potentially make the drug bind less or more to the DNA. So in the long term, other derivatives of our drug would have to be synthesized, which would allow us to see what the correct functional group to have like the perfect balance between killing off cancer cells but not affecting too many normal cells and having the least amount of side effects and being the most effective. So that's kind of where our drug comes into play. It's another step in figuring out what that perfect drug is that's going to have the best of all worlds.
Yes. So based on the different reactions and stuff that you use for the synthesis reaction, like how expensive would it be to actually make like a soluble form of the drug?
The question is how expensive it would be to make a soluble version of the drug. If you bought all the compounds, like for 1 gram of one of the reactants that we use, it was like $106. So if we make it in a lab setting, however, using the methods that we have come up with, it should not be quite as expensive, but we still don't know for sure.
Yes, some of the products from the reaction could have been bought, and in certain cases we use pre-made products, but in a mass production setting where you'd be using more of the products could be synthesized without human error in the lab, it would be less costly and more available to everyone. Yes.
How long does it take for like the tour you got?
Sorry, say that again?
How long does it take you guys to get to the
So I would say it took us about 4 to 5 weeks. We spent our first week kind of setting up the procedures and figuring out how we'd be adding the bromine element to our compound. But to get to where we got after 2 trials, we did attempt to make the step after step 2 twice. So those 2 trials took us 4 to 5 weeks, but so that if it was attempted again, it would definitely be much shorter. You'd be probably looking at like 1 or 2 weeks.
And as you do it more, and then it gets faster.
so why did you go with the YouTube as it's like
the question was why did we go with the nitrate group? Because it was more withdrawing. If it's more withdrawing, we don't want it to bind too tightly to the DNA as well, because then it might not come out of a patient's body quick enough. Because in order to have the least amount of side effects, it also cannot stay in a patient's body for too long. Because the drug doesn't know exactly which cells are tumor drugs and which cells are healthy. So it'll attack the ones that are closest. So it has to come out of the body quick enough to have the least side effects.
remember in class we talked about variables, right?
Yes.
So first, what are the dependent variables or the independent variables? Second, what are the variables that you think that if given a chance to kind of continue with research that you should include in research?
So I think our independent variable was the base 9-amino acridine compound that we started with, and let's see how I phrase this. I guess so. The dependent variable is the drug overall and the effect it's going to have on DNA binding, whereas our independent variable is the substituent group that we're adding to the compound. And could you say the second part of your question?
What are the variables that, given a chance, if you can continue this research that you would like to include in?
What other variables would you like to include if we continue this research? I think if you're able to continue this research, I would want to, given more time, obviously, get more time, I would add the be looking at different species that are described in these taxonomies. We'd be looking at DNA from mice, probably, if done other researchers, and maybe other species that are used in the laboratory.